Okay, so welcome everybody to our next Methods Live, and we're welcoming Abby Keller today, who's going to talk to us about a new tool for eDNA monitoring. Over to you, Abby.
Great, thanks. I'll just share my screen. Hopefully everybody's seeing this. Yeah, like Natalie mentioned, I'm Abby Keller. I'm a PhD candidate from UC Berkeley, and today I'll be sharing a little bit about an R package I developed called eDNA Joint, which will hopefully be a useful new tool for modeling environmental DNA data. The package is available on CRAN, and like Natalie mentioned, we have a manuscript in press about the package in Methods in Ecology and Evolution. Just to highlight, I think Natalie put this in the chat, but there are kind of two useful resources here. The first is a user guide for the package, has a bunch of example workflows, troubleshooting tips, kind of background information. That'll be a great resource. And then also I have a little GitHub repo with the slides I'm going to share today. I'm also going to be doing an example workflow in R. So if you want to follow along with the code, you can, but you also don't have to. So just kind of a quick overview, a roadmap of today's presentation so you know what to expect. First, I'll go through my motivation for developing the package and why I think it will be useful. Then I'll share kind of a few key features of package, more of a high-level overview. And you might have noticed on the title slide that the word Bayesian is in the title of the package. So the models that you can access through the package are formulated in a Bayesian framework. So a basic understanding of Bayesian statistics is kind of necessary for using the package. So I'll give just the world's quickest crash course on Bayesian stats and also refer you to some additional resources. I'll then go through an example workflow with endangered tidewater goby data from California. And this is one of two data sets that are embedded within the package, so you can play around with them as well. And it's useful for seeing how the input data should be structured. I'll finish with some troubleshooting tips and final thoughts. And then if all goes to plan, we'll have some time at the end for Q&A. So first, to start with the motivation for the package, environmental DNA or eDNA data has really exploded as a new source of information in the last decade. eDNA sampling is increasingly used in surveys of species distribution as a potentially sensitive and efficient monitoring method. And we've also seen this huge growth in private industry with dedicated eDNA services that really makes eDNA sampling gear and laboratory expertise more accessible. But unfortunately, software tools designed specifically for interpreting eDNA data have not kept pace with the broad availability of this new data source. We've seen this growth in the peer review literature of approaches that link eDNA data to quantitative estimates of species abundance. But these approaches are really confined to academic communities with the technical expertise necessary to develop these bespoke models. And to date, the occupancy model has really dominated the analytical landscape for interpreting eDNA detection data for single species. And this makes a lot of sense because the occupancy model is really useful for accounting for imperfect detection when assessing species presence. And often there's concern around false positive eDNA detections that really kind of presents a hurdle to adopting these approaches. So the occupancy model has been extended to account for false positive detections. And what I think is really important here is that there are multiple really accessible, easy to use software that could be used to implement occupancy models. So I think that kind of contributes to the ubiquity of this method. But occupancy models may not always be the most appropriate analytical method for interpreting eDNA detection data. The rate of detection can correspond to species density and not just occupancy. And really importantly, observations from non-genetic data sets, which from here on out I will refer to as traditional observations. So these traditional observations often spatially and temporally overlap with some or all eDNA observations. And existing software has not yet facilitated the integration of eDNA data with measurements made by other means. So eDNA is really a new type of information that presents new opportunities, but also new challenges with interpretation. So to address this problem, my co-authors and I developed a model that integrates multiple types of data in a way that they can mutually inform each other. And since the publication of this paper, I have kind of turned the model into an R package and added some more variations and made it more generalizable and accessible. So the idea is that both eDNA and kind of traditional data are generated from the same ecosystem state. So this model provides a formal way to jointly model them. And the primary purpose of this joint model is to use observations from both eDNA and traditional surveys to understand the relative sensitivities of the two survey types. And these kind of two data streams are used to jointly estimate parameters like the expected catch rate at a site. This is kind of like your expected catch per unit effort or kind of observation rate. And also the probability of a false positive eDNA detection, which I'm designating as P10 or P10. So the model is intended for use with replicated paired eDNA and traditional observations at multiple sites across the landscape. So your kind of primary sample unit are your sites. And ideally, you've collected data from sites with a range of species densities, including sites where the species is absent or at very low density. So you can kind of get a sense of the lower limit of detection. And then for each primary sample unit, so within each site, you have secondary samples. So for eDNA, this will be multiple water samples. And for traditional samples, this will be kind of multiple surveys and can be either discrete or continuous data. And then finally, for each eDNA secondary sample, so each kind of water sample, you'll have replicated observations. And these observations should be binary, so detection, non-detection, 1, 0. And we can think of these as our PCR replicates. So those are kind of the basic requirements, kind of the minimum set of information that you need to have to use the model. But there are multiple variations. And one of these allows for site-level covariates that scale the sensitivity of eDNA relative to traditional sampling. So maybe you've collected data on flow rates, temperature, or turbidity at your sites, and you want to see if these variables increase or decrease rates of eDNA detection. Or perhaps you have multiple kind of traditional gear types or traditional survey methods, and you want to account for the different kind of catchability or kind of observation rates of both of these kind of two methods or 2+ methods. And then finally, the model also allows for semi-paired data. And by semi-paired, I mean these are scenarios where you have traditional samples at only a subset of sites, but not all of them. So here you can make predictions about species density at sites where you've collected only eDNA data. So the function joint model is kind of the primary workhorse function of the package that will fit these models to your data. And there are also kind of additional functions that are used to help interpret the model output. So I'll do a demo today, and I'll be using data from a 2016 study on these super adorable, tiny, endangered tidewater goby fish in California. And here the authors also collected a bunch of information on kind of site-level variables, covariates. So as promised, I'll just share a few key concepts about Bayesian statistics. Like I mentioned, all of the models in the package are formulated in a Bayesian framework. So just kind of to make sure that you're using the package properly and interpreting your results properly, you kind of need a basic understanding of what the Bayesian framework is like. And at the bottom of this slide is a link to the section of the user guide that contains more information and more resources about Bayesian statistics. So the Bayesian paradigm differs from the frequentist paradigm in a few key ways. And for context, if you've done maximum likelihood estimation, that approach falls under the frequentist paradigm. But for Bayesians, all parameters are treated as random variables. So this means that they're encoded as a probability distribution. And this is different than frequentist statistics that assumes that parameters are fixed, and uncertainty is entirely attributed to our estimation of these parameters. And then similar to the above point, in the Bayesian paradigm, we characterize the distribution of the model parameters given the observed data, whereas in the frequentist paradigm, we characterize the value of the parameters most consistent with the observed data. And then kind of one last point, this is a really important one. The Bayesian framework encodes the idea of kind of a prior belief or prior kind of expectation of the parameter values that can be updated based on data. So here's Bayes' theorem put a few different ways. This is kind of the equation that underlies this whole kind of Bayesian framework. And the posterior is what we're trying to estimate. So this is our inference. These are the probability distributions that best describe the model parameters given the data. And the prior distribution goes into this calculation. So this is the kind of the way that we encode our prior beliefs about model parameters, and kind of the way that we specify this distribution can really affect our inference. So with the models in this package, you can kind of choose your own priors for some of the parameters, and it's really important to be kind of deliberate and thoughtful with how we're doing this. So there's kind of a lot of text on this slide, but I wanted to give a quick glossary of a few key terms because I'll be talking about them today. So MCMC, Markov chain Monte Carlo, is the algorithm that we use to kind of approximate or estimate the posterior distribution. And this MCMC algorithm generates samples of the posterior, which is just kind of a long string of numbers that we can use to summarize the posterior distribution. And we often run multiple chains of the MCMC algorithm since it's stochastic, so it's random. Every time you run MCMC, something different will happen every time. So we can run multiple chains and then kind of combine them to assess if the algorithm has converged. And then lastly, all of the models in the package are specified with a probabilistic programming language called STAN. So this kind of is one of the most popular kind of Bayesian implementation languages. And because the models are formulated in this way, you're kind of opening yourself up to the broader STAN ecosystem. You can kind of manipulate your kind of fitted model object with a bunch of different functions. Okay, so kind of enough background, and we're going to get to the more fun aspect of today's workshop. I'm going to do a kind of example workflow, and just want to highlight again, this link at the bottom here is the link to the GitHub repo that contains all of these slides, as well as the code I'm about to run through. So you're welcome to just kind of watch me do it, or if you want to follow along, you can check out the code there. Okay. So hopefully you're now seeing my R screen. Let me know if you're not. But yeah, so we're first going to, here we are in R. We're first going to load the package. Again, it's available on CRAN, and we're going to be using a few other packages in this demo. And the first step is to prepare the data. So making sure that your input data is formatted properly is really important for making sure that the functions are behaving as you expect. So it's kind of useful to spend some time with this to make sure we understand the format of this input data. So the Gobi data is one of the data sets that's embedded within the package, so you can play around with it as well. But just to look at the structure of this data, it's a list of 4 matrices. And the names of these matrices kind of shows what's in this data. So there's 2 matrices with our PCR or our eDNA data. We have our count data. In this context, these are our traditional observations. With the Gobis, the way that these traditional observations are collected, they use seine samples. These are kind of just nets that get swept through the water. You kind of sweep multiple nets through the water and count how many fish that you caught. So this is the kind of the count of Gobis in each net across the sites where you've collected data. And then in this scenario, the kind of authors that developed this data set collected some kind of site level covariates. So these are variables, environmental variables collected at all of the sites. So we can first look at the count data. So first look at the dimensions. We see that we have 39 rows. So this is the number of primary samples and the number of sites. So they collected kind of these net seine samples at 39 sites. And there are 22 columns. So this is the maximum number of secondary samples, the maximum number of seine samples per site. So just to look at the top of this matrix, we see that at site 1, so row 1, they collected 11 kind of seine samples, 11 net samples, and in each of these 11 samples, they caught 0 Gobis. At site 5, so row 5, they collected 18 seine or net samples, and they collected between 0 and 8 Gobis in each of these nets. So you'll notice there's a bunch of NAs, and this is because the authors collected different numbers of samples across each of their 39 sites. So the kind of dimensions of this matrix are defined by the site where they collect the most samples. And the way that we indicate this heterogeneity across sites is by filling in kind of the blanks with NAs. So this means that these NAs are meaningful. So for example, at site 1, they didn't collect a 12th sample. But this is kind of distinct from a scenario where they did collect a sample and they caught 0 gobies. So here NAs are meaningful, zeros are also meaningful. So here we see that at site 11, so row 11, they collected 22 samples, so no NAs here. So that's kind of, this is what defines the kind of dimensions of this matrix. So next move on to the eDNA or PCR data, and this is separated into 2 matrices, PCR-N and then also PCR-K. So N is the number of PCR replicates or the number of kind of PCR attempts or trials per water sample per site. So if you look at the bottom of this matrix, we see that at site 35, so row 35, they collected 2 water samples. And for each of these water samples, they had 6 PCR replicates or kind of trials. At site 38, they collected 8 water samples and kind of they were consistent here and collected collected 6 PCR replicates. And again, we're using these NAs to account for heterogeneity across the sites. Kind of looks like here their maximum number of water samples they collected was also 22. So just to kind of think more about the indexing of this matrix, here at kind of site 4, row 4, water sample 6, column 6, they did 6 PCR replicates or kind of PCR trials. PCR-K is the number of successes. So these are kind of like binary detections of the number of replicates, how many detections were there. So again, looking at the bottom of this matrix, at site 35, row 35, of the 2 water samples they had 0 positive PCR detections. Whereas at site 38, they had 8 water samples and they ranged from 0 to 6 positive detections per water sample. Again, just to highlight the indexing here, at site 4, row 4, water sample 6, column 6, they had 5 positive detections of the 6 kind of trials. So when you input your data to the package, it'll kind of automatically run a bunch of tests to make sure that your data is formatted properly. But if you kind of want to do a sanity check for yourself, that's probably useful. So again, the NAs are meaningful. They kind of designate or just define the heterogeneity of the sampling effort across your sites. So you want to make sure the NAs are in the same place for the 2 PCR matrices. And then all of these matrices should have the same number of rows. So this is the number of sites to make sure that's true. And then previously in the presentation, I mentioned that the package works for semi-paired data. So again, this is the scenario where you've collected eDNA samples at all sites, but only like traditional samples at a subset of these sites. So here in that scenario, you would kind of keep the same number of rows in your kind of traditional sample matrix, but you would fill in the empty sites with NAs. So again, NAs are meaningful. And I have it, won't go through an example of that here, but there's an example of how to kind of implement these models with semi-paired data in the user guide. Okay, so these kind of PCR matrices and count matrices are the minimum requirements to use package. But there's also these authors collected site level covariate data. So this is kind of environmental variables collected at each site. They had information on salinity, filter time, which is the time it takes for the water to pass through the filters, which is kind of a proxy for turbidity. They have density of other fishes. Habitat size, so this is they collected samples at kind of wetland and lake type habitat, so this is kind of the acreage of the sites. And they have this binary kind of presence absence variable for vegetation. And you'll probably notice that some of these numbers are negative, which is kind of confusing. What does negative other fishes mean? This is because all of these first 4 continuous variables are normalized. This means that the mean of these columns are 0 and the standard deviation of these columns are 1. And the reason that we do this is because these variables are entering the model through kind of a linear regression form. And you want to kind of make sure that the different variables are on the same order of magnitude. And also having this kind of normalization, mean of 0, standard deviation of 1 helps with kind of the estimation algorithms, kind of the stability of those algorithms. So I definitely recommend if you have site level covariate data and it's continuous, I would definitely recommend normalizing that before you're using these functions. Okay, so now hopefully we understand the input data. We're going to fit the model using the function join model. So again, this is kind of the primary function of this package that will be fitting these models to your data. And there's a bunch of arguments, but just to kind of go through the main ones. The first is data. So this is the data we just went through, our list of matrices. Then we can provide a vector of our site level covariates. So you can input data with all of these covariates, but maybe you want to run the model on just a subset of them. So here is where you can kind of indicate which of these variables you want to include in the model. You'll then specify the family. This is kind of similar if you've used the LM, like linear model functions in R. This is the kind of probability distribution that describes the data generating process for the traditional observations. So here, this is kind of the net, the same count data. The options here are Poisson or negative binomial for count data, and then a gamma distribution if you have continuous traditional observations. The next argument is the prior specification for P10, which is the probability of a false positive. I'll talk more about this later, but just to highlight that the default specification will be this vector of 2 numbers, which are the shape parameters for a beta distribution. So again, this is the prior for the probability of a false positive. The kind of the default specification here is one that's is not particularly informative. But again, I'll be touching on this more later. And then the last big argument is a logical value, so true or false, which indicates whether you have multiple traditional gear types or survey types. So here is the actual kind of implementation of this function. We have our data. I'm just going to run this on a subset of our site level covariates, so just the filter time and salinity. We're going to use a Poisson distribution to describe the data generating process for the same, the net samples. We're going to stick with the default specification for the P10 prior. We only have 1 traditional survey type, and we're going to be running multiple MCMC chains, so 4 to be specific. And just to speed up the calculations, we'll be using multiple cores on my computer, so each chain will be running in parallel on this computer. So we can kind of watch as the kind of algorithm progresses. We see the chain starting on each of the 4 cores. We can kind of, it's a little bit grayed out here, but you can see the progression of the MCMC sampling, each of the iterations. And just for context, I'm running this on a cluster. So if you're running these functions locally, it looks like it just finished. So this might be faster than if you would have run it on your own computer. You might be aware, but Bayesian methods are particularly computationally intensive and slow. So if things are running longer for you, don't be surprised. But yeah, so it looks like it worked. There are more arguments to this function. Most of them are related to customizing the MCMC algorithm, but hopefully for most applications, you can stick with the defaults. So when we ran the model, we returned this GoBFit covariate 1 object. If you look at the names of this object, or this return object, is a list of 2 things. The first is the actual fitted model. So this kind of object contains all of our posterior samples. And again, it's of the class stanFit. So because all the models were specified in stan, you can kind of open yourself up to all of the functions in the rstan package to manipulate this object as well. And then the second element of this return object list is our initial values that we use in the MCMC. So the algorithm has to start somewhere. Ideally, you'll run multiple chains, start the algorithm in different places, and then it will converge. All the chains will converge in the same parameter space. So it's useful to kind of document what the initial values were, as kind of understanding whether the algorithm is converged. So this is of length 4 because we had 4 chains. So this is documenting initial values used in each of the 4 chains. Okay, so now that we've fit our model, kind of the question becomes, is it a good one? And a way to think about this is through a model selection exercise. So in this first model, we use salinity and filter time as the kind of covariates that affect the rate of eDNA detection. But perhaps we want to see how this model compares to others that contain different covariates. So here we're going to, instead of the salinity and filter time, we'll use this kind of vegetation, presence, absence, binary variable to compare. I'll start running. And then here I've also designated verbose as false. So we see that it doesn't print out a bunch of messages if you want to avoid kind of clogging up your workspace. But I guess while this is running, we'll use the function joint select in the package to compare our 2 models. So with this function, joint select, there's just one argument, which is a list of our model fits. So the first one here is the model with the filter time and salinity. The second one is with the vegetation site level covariate. And this function is performing model selection with leave one out cross validation, which is kind of a method used to understand how well a model predicts new unseen data. And this is measured with the ELPD, which is the expected log predictive density. And we usually want this value to be higher. So this indicates that a model is more predictive, better at predicting out of sample data. So here we see that model 1 has a higher, is more predictive, higher ELPD than model 2. You could kind of like continue this exercise for a bunch of different combinations of covariates to see which model fits the best. But for now, we'll just kind of stick with model 1. Again, this is the one that contains salinity and filter time as the covariates. Okay, so we've fit our model. We've decided which one we think is kind of the most parsimonious model for our data. And now we want to kind of investigate what our inference is, and we'll do this by summarizing the posterior. So here we can do that with the function joint summarize, and we can run this on our model fit, and we can select which parameters we want to summarize. So here we're going to be looking at P10, which is the probability of a false positive eDNA detection. And here we see the kind of the mean of this, the marginal posterior distribution for P10, the standard deviation, the lower and upper bounds of the 95% credibility interval. And then these last 2 values are related to kind of how well the MCMC algorithm performed. So NF is the effective sample size and is kind of a measure of the efficiency of the MCMC algorithm. We also have R hat. For the effective sample size, higher the better. Then for R hat, this is kind of the most important diagnostic usually in MCMC. It's a measure of how well the 4 different MCMC chains converged. So ideally, you want it to be less than 1.1, and then even more ideally less than 1.05. So it looks like this parameter, the MCMC algorithm converged for this parameter. If you're ever writing a report or a paper where you're including Bayesian results, this is kind of the main diagnostic that you should be reporting kind of as evidence that your results are reliable and that you can trust how the MCMC algorithm performed. So we can also kind of plot these posterior samples as a density plot, and I'll zoom out a little bit even more. So again, Bayesian statistics, the parameters aren't described by a value, but rather a probability distribution. So this is kind of the probability, the kind of marginal posterior probability of the probability of a false positive, P10. So we can see that it's most likely between about 0.001 and 0.007. So this is kind of our way of quantifying uncertainty with the estimate of this parameter. We can also look at a trace plot of this parameter, and a trace plot kind of traces the progression of the MCMC algorithm. So here on the x-axis is the MCMC iteration. So this is kind of as the algorithm is moving over time. The different colors are the 4 different MCMC chains. And then the y-axis is kind of the parameter space that the algorithm is moving around. And I just wanted to share this because I think it's important to, trace plots are really important for helping diagnose MCMC problems and also just kind of ensuring that the algorithm is functioning as you expect it to. And this is what you're looking for. So we see that the 4 chains are completely on top of each other. We would describe this as being stationary. So this means that the kind of iterations are moving around the same mean and have about the same variance over time. I've heard this described as being a fuzzy caterpillar. So if your trace plots look like a fuzzy caterpillar, then you're probably in good shape. But again, this is, I think, getting familiar with producing trace plots and interpreting them will be really useful for kind of interpreting your Bayesian results, and especially helpful for troubleshooting and diagnosing problems. Okay, I'll zoom back in. So we just summarized the posterior for P10, so it's the probability of a false positive. And now we're going to look at mu. So this is a parameter in the model that is the kind of expected catch rate, or observation rate at a site. So this is kind of like the expected catch per unit effort if we think of it as being a random variable rather than a fixed variable. So we see that we have an expected catch rate for all of our 39 sites where data was collected. We see that there's a wide range of expected catch rates, kind of a proxy for species density. And we also see that all of our hats are, when rounded, equal 1. So it looks like we're in pretty good shape there. The next thing we'll think about is interpreting the site level covariates. So again, we include these covariates because we expect them to kind of scale the sensitivity of eDNA sampling relative to traditional sampling. And in the model, beta is this kind of site level parameter that scales the sensitivity of eDNA. So it has this kind of subscript I, where I is a site. And it follows this kind of linear regression form where we have different coefficients and then the values of our 2 covariates. As beta increases, the sensitivity of eDNA sampling decreases. So if a positive regression coefficient would indicate an inverse relationship between the value of the variable and the sensitivity of eDNA. So we can now, alpha is a vector in this case of length 3. So we can look at, summarize the posterior for alpha. So again, alpha 1 is the regression intercept and kind of indicates the relative sensitivity of eDNA at the average site. And then alpha 2 is the regression coefficient for filter time. We see that it's positive, so the mean is greater than 0. The entire 95% credibility interval is also greater than 0. So since this is positive, it means that at sites where the filter time is longer, so kind of sites that are more turbid, the sensitivity of eDNA is lower. Looking at our third kind of element of the alpha vector, this is the regression coefficient for salinity. We see that the mean and the entire 95% credibility interval is negative because of this inverse relationship. Since this is the coefficient is negative, this means that sites with higher salinity are eDNA is more sensitive. So I think these 2 results kind of made a lot of sense to me. So again, sites with a longer filter time, the water is more turbid. This tends to mean that there's more PCR inhibitors in the water. So if there's more PCR inhibitors, the sensitivity of eDNA is lower. And then conversely, with salinity, we see a different relationship where at sites with higher salinity, there's more salt in the water. More salt often means, salt is kind of a preservation agent for DNA. So the DNA is lasting longer in the water, and therefore eDNA samples are kind of more sensitive than kind of an average salinity level. So really kind of the goal of this package, or one of the goals of this package, is to understand the relative sensitivities of the different survey methods. So to kind of make the values of these estimated parameters more concrete, we can use this function detection plot. So this is calculating the number of survey units necessary to detect species presence. And by detecting presence, I mean producing at least 1 true positive eDNA detection, or catching at least 1 individual in a traditional survey. So we can make this calculation for the average site. So again, looking at our linear regression in the model, because we normalized our data, the mean filter time will be 0. The mean salinity will also be 0 across all of our sites. So if we're going to be making this calculation for an average site, we'll be multiplying these two coefficients by 0, so that we're just left with the intercept. So here we're I'll start running this. So we're going to make this calculation using our model fit, a range of expected catch rates. Here we're designating that we're making this calculation at the average site. So we have this vector of two numbers that indicates that we're calculating at 0 filter time, 0 salinity. And again, this calculation is it's calculating the number of survey units necessary to detect presence. And then here this will be at with a 90% chance, so 0.9 probability. I'll zoom out just a little bit. So here is the result of this. On the x-axis is the expected catch rate. So this is the proxy for species density, but treated as a random variable. So given an expected catch rate, we see on the y-axis how many survey units do you need to collect to detect presence. And the different colors correspond to the two different survey methods. Just to highlight this a little bit further, so a more sensitive method, you would need fewer survey units to detect presence. So here we see that eDNA is more sensitive than traditional sampling in detecting presence across the entire range of species densities or expected catch rates. So we made that calculation for the average site, but maybe we want to understand how this would change for a site that's not average. If we're collecting samples across the landscape at a variety of sites, how will the sensitivity of eDNA change under different circumstances? So here we're going to be making the same calculation, but at a higher filter time. So at a site that's a little bit more turbid. So again, thinking about this regression equation, we're going to be calculating for the average salinity. So that's the alpha 3, but we're going to calculate it for a higher filter time, which is multiplied by the second element of this alpha vector. So this gets input here with this cov-val argument. And the first element of this vector corresponds to the filter time. So here we see in this scenario where we're calculating for a site with a higher filter time, we lose this increased sensitivity of eDNA, where again, on this x-axis is the expected catch rate. So for given a catch rate, we're calculating the number of survey units. So this here is number of water samples or number of sane samples necessary to detect species presence. And now it takes eDNA is no longer more sensitive per sample unit than the traditional samples. So we can do the same calculation for increased salinity. So now we're going to be keeping the filter time at the average value and increasing just the salinity value. We'll do this again here, specifying the value of the covariates with this vector. And then I think if we were to compare these this plot to the first plot that we did at the average site, we would see that this pink line is lower. So now sites with higher salinity need fewer water samples to detect presence because eDNA is more sensitive. So this function helps us make the relative sensitivities of the two methods more concrete, but also is helpful if you're planning a survey and you want to understand what effort should you expend, how many samples should you collect. So this gives you a sense of what is necessary to detect presence with your two survey methods. We're somewhat low on time, so I'll move through this last bit somewhat quickly. But if you recall, we ran the original model with the default specification for the prior for a probability of a false positive. And just to plot what this looks like. So this is the default distribution for P10 that you use in the model. And this is relatively uninformative. So having this prior indicates that we expect the probability of a false positive to be less than about 0.2. So in this distribution, most of the probability density is less than 0.2, which hopefully for most applications, you can expect that your rate of false positives is quite low, hopefully lower than 0.2. But you can also, it doesn't have to be, you don't have to just choose a somewhat uninformative prior. If you have information that can inform the prior, you should use that. So an example of this, let's say you collected a bunch of negative controls. Let's say you have 25 negative controls. You can kind of expect that your probability of a false positive is less than 1 divided by 25, so 0.04. So you can make a more informative prior that reflects this belief that the probability of false positive is low, less than 0.04. So again, this is kind of more informative and reflecting your expectation that the probability of a false positive eDNA detection is quite low. I think in both of these scenarios, it's kind of good practice to do a prior sensitivity analysis. So the goal of this would be to see how sensitive your inference is to the choice of your prior. Ideally, your inference is driven more by your data than by the prior. So what you would do here is run the model multiple times with different prior specifications and see how sensitive your inference is to those choices. So I'll just skip through this because I've already ran this. But here's an example of this. Do that again. So on the left, there are 3 different specifications of the prior. The different colors correspond to different prior choices. And then on the right is the posterior under each of these circumstances, kind of with the same x-axis. So this is really just to show this would be an example of where your inference or your posterior inference is not sensitive to the choice of prior and is more driven by the information in your data than, again, your prior choice. So definitely recommend doing a prior sensitivity analysis if you're trying to kind of inspect the robustness of your implementation. Okay, I have just one last slide, and then hopefully we get to questions. Go through this quickly. Ideally, you'll run the model in your data. It'll work the first time, and it'll be wonderful. But in case that doesn't happen, there are some troubleshooting tips. Down here at the bottom, this is a link to a much longer version of troubleshooting tips. But yeah, a few suggestions are to think about different customizations for the MCMC. I definitely recommend the package Shiny Stand. That's useful for creating trace plots and diagnosing different problems. And also here is my contact information. If you ever run into any problems, please email me. I'm always happy to hear from people who are using the package. It's useful to figure out what problems folks are running into, whether I can write better documentation, or even if there are any bugs, it's nice to know about that as well. Okay, so just thought I would finish with this photo of the mouth of the Columbia River. Quite relaxing to look at, and see if anyone has any questions.
That was excellent. Thank you so much. That's such a cool package. I'm really excited to see the paper when it's out. Let me pin you for everybody. There we go. So questions wise, if people just paste them into the chat and then I'll ask Abby. We've got one question so far that was pasted fairly early on, which is just, and you may have answered this later, but I'll ask anyway. So is the model scalable to entire communities? For example, vertebrate communities sampled with traditional methods and water sampled with eDNA.
Yeah, in that scenario, you would probably have to run the model multiple times for each member of the community. So I guess right now there's no way to kind of account for the kind of covariance among species in a community. But if I'm interested in expanding this package, this is kind of just one dimension of eDNA. So if anyone's interested in contributing code and would be interested in doing a more community level implementation, I'd be happy to do that.
Cool. So Luciano has a question. Do you want to unmute yourself, Luciano, and ask?
Yes, thank you very much for the presentation, Abby. I was wondering if it would be more informative to include, or if it's possible to include copy number um, in these type of models instead of just presence and absence.
Yeah, again, that is kind of to the same point previously. There are kind of many dimensions of eDNA data, and we just focused on just kind of presence, absence. And that was mostly because the model where we developed this, or the paper where we developed this model, we just found a stronger relationship between species density and kind of the rate of binary detection than the kind of relationship between species density and copy number. But yeah, again, I'm definitely interested in expanding the package, and that would probably be like the lowest hanging fruit, is to be thinking about copy number rather than presence absence. So yeah, again, email me if you're interested in joining, but that is definitely kind of a priority for expansion.
Right, Abby, thank you very much.
Any more questions? So I guess my question is, so what are your next steps? So what are you planning on doing next with this?
Yeah, when the paper gets published, I'm gonna if no one here has heard of the kind of community programming organization called Our OpenSci. This was kind of my step into programming actual software. It went through a peer review process before kind of submitting it as a paper in methods. So it's kind of this kind of volunteer software community that helps kind of develop packages. So yeah, my next step is I have a blog post already written, so I'm going to publish it when this paper gets published as kind of a call to action to see if, for now, like I was the only person writing all of the code for this, so I, can't do everything myself. So I would love to have this more of a collaborative effort, adding on things like the two folks here mentioned, more of a kind of community level, accounting for community, like metabar coding data, and then also continuous qPCR data.
Cool. Yeah, we love our OpenSci. If anyone's interested in knowing more about that, I've pasted the website into the chat. But yeah, it's a great community. Does anyone else have any questions? Oh, sorry, just see one. So great talk from Gina Simons, and says, in your opinion, how long would it take to define suitable priors? Got only a few months left of my PhD, but I'd love to try and use this.
Yeah, I think the first step would be to kind of stick with a quite uninformative prior, especially if you don't really have an expectation of what the probability of false positive would be. And typically that works. I think the one scenario where you really need to be thinking about a more informative prior are scenarios where your species is quite abundant across the landscape. So the probability of false positive is informed by like the zeros in your data sets. So if you have sites where the species is absent or very low density and you have a bunch of zeros, that's kind of the information that informs the false positive rate. So I think probably the first step was just to, if your species is more kind of about early detection or like lower, kind of like a lower abundant species, hopefully there's enough information in your actual data to inform the probability of false positive using an uninformative prior. But if that's not the case, again, thinking about how to leverage negative controls to think about your expectation for a false positive rate.
Cool, thanks. Anybody else like frantically typing something? If you just maybe put your hand up or put a quick message in the chat so that we know to wait. Here we go. One from Merrin. It would be nice if you or your lab could have a Google sorry, I can't speak today. A Google group to post questions as we go working with the project. It could be that many people have the same questions or doubts. Do you have a plan to write anything like that?
That sounds like a great idea, and I will totally do that. I mean, as of now, for the people that have found the package, just been emailing back and forth, but you're right. I'm sure I've already kind of repeated the same answers to all those people. So having a way to have kind of a document of questions and answers would be really useful. So I'll do that, and I will figure out a way to kind of share where that is.
That's a great idea. Yeah, FAQs are always good. I mean, you could often stick things like that on GitHub potentially if that's where people are gonna do things.
Yeah, good point.
Okay, so I'm going to assume that we're done with questions. But if anyone has any more questions, you've got Abby's contact details, and also might want to wait until the paper comes out to see if those answer your questions as well. But otherwise, like, thank you, Abby. That was brilliant. It was really cool and a really exciting tool that hopefully sounds like lots of people have already thought of ways they're going to use it. So that's excellent. So thanks everyone for coming, and hopefully see you at the next one of these. Bye.